The first thing we should notice is the expression inside the square root. We have y cubed plus 8, and 8 can be written as 2 cubed. That means this is a perfect opportunity to use the sum of cubes identity. Remember, a cubed plus b cubed equals the quantity. A plus b multiplied by the quantity, a squared minus a multiplied by b plus b squared. Applying that identity with a equal to y and b equal to 2, we get y cubed plus 8 equals the quantity, y plus 2, multiplied by the quantity y squared minus 2y plus 4. Now, let's substitute this factorization back into our original equation. The equation becomes y squared minus y plus 6 equals 2, multiplied by the square root of the quantity y plus 2, multiplied by the quantity y squared minus 2 plus 4. At this stage, the equation still looks complicated, so let's make it much easier to read by introducing two new variables. Let m equal y plus 2, and let n equal y squared minus 2, y plus 4. Now let's see what happens if we add m and n together. We have the quantity y plus 2 plus the quantity y squared minus 2y plus 4. Combining like terms gives us y squared minus y plus 6. Notice how this is exactly the expression on the left side of our equation. That means we can rewrite the entire equation as m plus n equals 2, multiplied by the square root of m multiplied by n. This is much simpler. Now, move everything to the left side, giving m plus n minus 2 multiplied by the square root of m multiplied by n equals 0. Look carefully at this expression because it has a very important pattern. Recall the identity that the quantity square root of m minus square root of n whole squared expands to m plus n minus 2 multiplied by the square root of m multiplied by n. So our equation becomes the quantity square root of m minus square root of n whole squared equals 0. The only way a square can equal 0 is if the expression inside the square is 0. Therefore, square root of m equals square root of n. Since both sides are square roots, we can safely square both sides, giving m equals n. Now replace m and n with their original expressions. We get y plus 2 equals y squared minus 2y plus 4. Let's bring everything to one side. Subtract y plus 2 from both sides, and we obtain y squared minus 3, y plus 2 equals 0. Now let's factor this quadratic. We need two numbers whose product is 2 and whose sum is negative 3. Those numbers are negative 1 and negative 2. So the equation factors as the quantity y minus 1 multiplied by the quantity y minus 2 equals 0. By the zero product property, either y minus 1 equals 0 or y minus 2 equals 0. Therefore, our possible solutions are y equals 1 and y equals 2. But whenever an equation contains a square root, it is always good practice to check every solution in the original equation. Let's test y equals 1. The left side becomes 1 squared minus 1 plus 6, which equals 6. The right side becomes 2 multiplied by the square root of 1 cubed plus 8, which is 2 multiplied by the square root of 9, giving 6. So y equals 1 is a valid solution. Now let's check y equals 2. The left side becomes 2 squared minus 2 plus 6, which equals 8. The right side becomes 2 multiplied by the square root of 2 cubed plus 8, which is 2 multiplied by the square root of 16, giving 8. This solution also satisfies the equation. Therefore, the complete set of real solutions is y equals 1 and y equals 2. This problem is a wonderful example of how recognizing a hidden algebraic identity and making a clever substitution can transform a difficult-looking radical equation into a simple quadratic equation.